So let's look at an example of one of the calculations that they do with the case of a continuous distribution of charge. Okay? So the simplest case, a line of charge, so charge uniformly spread on an object that is very thin, and that object has a length L, say. So a continuous distribution of charge. So there is a rod that has some charge. That rod has a total amount of charge Q, and that rod has a length L, actually 2D. Yeah. So this is 2D. The whole length of the rod, we're going to call it 2D. And we're looking at a point P over here, and we want to calculate the electric field produced by that continuous distribution of charge on that rod. So once again, you have to think about the contribution of each segment of the object, right? And if you look at the contribution of the electric field at point P due to this charge, you will notice that that should be a little vector, delta E, let's call it, and should be pointing that way. But then the next thing to realize is that the amount of charge on that bar that is symmetrically located on the other side of the axis contributes with the same amount of electric field and in the same direction. So the problem that we solved with the three charges should come to mind, right? Where we have the electric fields pointing in those directions, and the y component of those fields are going to cancel. Right? So if we were to calculate or try to calculate the net electric field at this point, that will be a big vector here, E, right? And the way you would calculate it is you will look at the different, you would sort of mentally divide the rod into sections. Each section contributes with an electric field with a particular magnitude depending on the distance, right? So if you call this section I, for example, then this distance over here is Ri. So the electric field contributed by that amount of charge I located up there would be K times the amount of charge that you put in there, that you have in that section. This has an amount of charge delta Q, divided by the distance between that section of the rod and the point P where you're at. So R sub I squared. That's how much this vector is. Let's call that delta E sub I down here. That's the magnitude. The direction will be given by that angle theta, which you can figure out from D. That's D, and this is X over here. Okay, so let's say tangent theta is D over X. Okay, so because the electric fields are going to cancel in pairs, the y components of the electric field are going to cancel in pairs. You would always find to every section of the rod up here, you will find a section of the rod below that cancels the y electric field of that charge. Okay, so what I'm trying to say is that the net electric field, you only have to worry about adding up the contributions on the x direction of all of the electric fields of the little pieces, right? So for the net electric field, what you want to do is add all of the contributions, but in the x direction. So you'll have to multiply them by the cosine of the angle, particular angle that sec element here makes with the horizontal. Okay, so you're adding all of those components. The electric field produced by a section below that one will be in the x direction will be another vector. So you add all those vectors, all those little segments, and that's your final electric field, right? So I'm going to write a few more lines and then give you the final result. The electric field of that section I, labeled by I, how much is that? Well, we wrote it over here. that is k delta q divided by the distance, which is d squared plus x squared, right? And how much charge do you want to put there? Well, the amount of charge that you want to put there will depend on how long is the section that you're considering, right? So that will be k times the linear charge density of that rod times delta y. What is delta y? Delta y will be the length of that segment. That is delta y. And divided by d squared plus x squared. Okay? So this sum basically has the terms k lambda delta y divided by d squared plus x squared and multiplied by the cosine of theta sub I, which is the adjacent x over the hypotenuse, which is square root of d squared plus x squared. Now I shouldn't call it d because that section of the rod is actually at a location y. Remember that we're going to change that location to add the contribution from everybody. So the contribution of a segment here will be dependent on the y of that segment. So this is y sub I. Right? So let's put that explicitly here and here. So this is y sub I squared. And the same here, y sub I squared. Okay? Okay, I'm almost done with that part. Y sub I squared, y sub I squared. Okay. So now you have an expression that tells you how much is the contribution, how much is the electric field in terms of the contribution of the little segments in which you can divide this rod. Those segments are defined or characterized by what is their height on the x-axis, where they are located along the x-axis. That's what the y sub I gives you, right? And each one of those sections has a charge lambda delta y. Okay? And we're looking at the x component of the electric field produced by every little section. Excuse me. So that's why that expression is like that. So the next step is to turn this already almost in the form of an integral. If you haven't taken integral calculus, don't worry about this last step. But this is going to end up looking like this: k lambda dy over y squared plus x squared to the 3/2 power. And there's an x up here. And you're integrating, you're adding this expression from minus d to d. Okay. So the final expression, I'm not going to do the integral here, but the final expression is this one. And then again, we're going to play the game of looking at what does that expression turn into when you're far away from the rod, when you're close to the rod, and so on. So here's the final expression. It has a d over here, and the square root of d squared. Okay, let me write it a little different. So that final expression is going to have, the book calls it d, I call it x here, x and x squared plus d squared. Yeah, okay. It should be correct. All right, so this is the electric field of a finite line of charge. So the parameters of that line of charge are that the length of the line of charge is 2d, and I'm sorry your book called it L, so I hope you don't get confused about the factor of 2 showing up there. And you are at a distance x from that rod, from the middle point of the rod. Okay, that's what you have to keep in mind when looking at this equation. That's what those variables mean. So what happens when you are far away from it? So if your distance, x, is much bigger than the characteristic size of this rod. So in the denominator, the x is much bigger than the d, so x squared is going to be a lot bigger than d squared. So you can ignore d, and you get the electric field is kq over x squared, which is the same as for a point particle. So you have a rod like this one, and it has charge in it, and you put this rod 3 blocks away from here. Again, that little rod is going to look like a point particle if you're far away from it. So that's what you should expect. Then the other limit is when x is much smaller than d. So in this limit, the rod is, for the x much bigger than d, the rod is tiny and you're out here, right? The other limit that I want to look at is when you're really close to it. So the rod is here and you're really close to it. That's your x. And the rod has a length 2d. So what does this equation turn into? So again, if x is much smaller than d, then you can ignore the x next to the d. The d is much bigger than it. So your expression would look like this. Okay, q over. There's nothing you can do about this x out here. That is determining when x is small, that's making the electric field big, which is what you expect. But the square root, you can just simplify it by ignoring the fact that there is an x there. So that is d squared square root, that's a d, right? So you get k over x. And q over d, what is q over d? Well, q over 2d is what? We have a special name for that charge per unit length. That is lambda, right? It's the total charge divided by the total length of this thing. So this is k divided by x times 2 lambda. That's what it becomes. So if you're really close to a linear distribution of charge, if you're really close to it, notice that the electric field does not change as x squared. As you increase your distance by a factor of 2, provided that it's small compared to the length of the rod, your electric field is not changing by a factor of 4, which is what you expected from a point charge. If you're close to a point charge, right here, and you decrease the distance by half, the electric field goes up by a factor of 4 because of the d squared in the denominator, right? In the case of a long line of charge, when you decrease the distance by half, your electric field only goes up by a factor of 2, not 4, right? That's what this expression is telling you. The dependence with x squared, it's gone. It only depends on x. So this approximation, this case where the length of the rod is much bigger than the distance at which you are, it's called the infinite line approximation. It would be the case, that would be the expression that you would get every time you have a location that is really close to a line of charge. Now, why would you expect that would happen? That the strength of the electric field near a distribution of charge, long distribution of charge like that, why would you expect that the electric field behaves that way? The electric field here points that way, and as we just derived, sorry that I changed the notation here a little bit, didn't realize that. The electric field is, in the notation that you're seeing there, is 2k lambda divided by r. So r is your distance from the middle of the rod. That's your r, right? So why does the electric field depend linearly with distance? You're getting closer and closer to charges on this rod. Wouldn't that grow like 1 over r squared, which is what happens with point charges? The reason is we have the tools to understand that from the example that we did with the 3 charges. So what happened when you move really close to the 3 charges? The electric field, the contribution to the net electric field coming from the top and the bottom charge, they tended to cancel each other out, right? Because you're so close that the electric fields are almost aligned. One pointing down, the other one pointing up, right? So that tells you that above a certain angle, right? If you have a very long line of charge and you're standing in front of it, above a certain angle, the charges that are past that angle, up there or below, their electric fields at this location where I am, they tend to cancel each other because they're so vertical, right? That charge is way up there, and if I look up there, it's almost like looking at 90 degrees. So the electric fields are canceling each other completely. So you can think of sort of drawing a line, some sort of angle or effective angle at every location, at every distance that you are from an infinite. This is infinite, right? This is going up and down, above which you can ignore these charges. There are the ones that are at a location on this line that are above a certain angle. The same for the ones that are below that angle. You can ignore those. Okay, so how much charge is it going to affect or produce or contribute to the electric field at any particular location? If you are at this distance, the amount of charges that are going to contribute are the ones located at a distance delta, let's say L. Let's say L1. And if you are at this location, the amount of charges that will really contribute to the electric field at your location will be the ones contained in that area, which has a length L2. So this is electric field 1, which has some value, and electric field 2 is here. So the electric field at point 1 should be, this is all sort of heuristic or approximate analysis, the electric field at point 1 should be dependent on the amount of charge that are contributing to it, and those charges are contained in a length L1, right? So Q1 divided by the distance that you are at, which is R1 squared. The electric field at point 2 should be KQ2 divided by R2 squared, and what I'm saying is that Q1 and Q2 are related by this. This is the linear charge density multiplied by L1, and this is K times the linear charge density multiplied by L2. How does L1 and L2 change? How does the L, the amount of charge, the length of the charges that are contributing to the electric field, how does that change as you move closer to the line of charge? What happened to L1? When you move from point 1 to point 2, that length decreases. Right? So that L should be proportional to the distance at which you are from the rod. Right? So that L should be proportional to your distance. So your electric field at some location depends on like this. K lambda. That L is actually some constant proportional to R, and you're dividing by R squared. R and R cancels. And there you have it. The electric field does not depend as R squared, it depends as linear R, 1R, because the amount of charge that contributes to the electric field as you get closer to a line of charge, the amount of charge that effectively contributes is going down also. Because if you're really close, very quickly, charges that are above or below you do not affect you at all because they're fighting against each other. The electric fields are opposite to each other. Okay? So that is what's behind that interesting dependence on linear or inversely proportional to the distance.